All right. Good. All right. Hey everyone, today I'm Ethan, and today I'm going to be talking about CoolerSpace, which is a domain-specific language for color programming. Before I get into the contents of the paper, it's probably a good idea for me to talk about the field of color science and what we term the term color program to mean. In very broad terms, color science is a study of human color perception and cognition. Applications are wide, and they include graphics, historical preservation, photography, color reproduction, photogrammetry, among many, many others. And in our paper, we specifically define color programs as programs that manipulate visible spectrum and color data. Examples of color programs include color blindness simulation, white balance algorithms, otherwise known as chromatic adaptation transforms, and digital simulations of pigment mixing. Unfortunately, the current ecosystem for writing color programs kind of sucks. Color programs are particularly prone to uncaught errors. Bugs in user code can easily pass compiler or interpreter scrutiny, and these bugs often require domain-specific knowledge to avoid and manifest themselves in rather subtle ways. As such, logic bugs often remain uncaught both by compilers and by users. So if you've used any photo editing software or painting software before, you've probably seen this slider here, or some variation of it anyways. It's an sRGB slider, or an RGB slider. It uses just the amount of red, green, and blue primary used to display a color. And you've also likely seen HSV sliders as well. Instead of adjusting amounts of R, G, and B, you instead adjust amounts of hue, saturation, and brightness. So what's interesting here is that the HSV value below and the RGB value above are numerically different, but they actually represent the same color. So HSV and RGB are different encodings of color, and in color science, we refer to these encodings as color spaces. And a lot of people are only really aware of these two color spaces. However, there are a truly massive amount of color spaces out there, and these are the only ones that I could list. These are only the ones I could list off the top of my head. So, and on top of that, failure to keep track of the color space of image data can lead to subtle bugs. Take image compositing as an example. Let's say I want to place this poorly green screened kiwi near Pasadena City Hall. However, the kiwi image is encoded in the ProPhoto RGB space, while the photo of Pasadena City Hall is encoded in the sRGB color space. In order to composite these two images together, programmers should convert the kiwi photo from ProPhoto RGB space to sRGB space first, as seen below. But nothing's really stopping programmers from skipping the color space conversion entirely. Even though the image of Pasadena City Hall is encoded in sRGB and the kiwi is encoded in ProPhoto RGB, this segment of Python code runs without issue. In Python, these images are represented simply as arrays. As such, if the dimensions of the two images match, and they do after some transformations, Python libraries take no issue with executing the buggy code. The incorrect implementation outputs the following image. So, as we know, performing arithmetic on color data of different color spaces is physically meaningless. It's no op. However, the produced output is still approximately correct. For reference, this is the output of the correct implementation. The difference between the two is rather subtle. Without a direct comparison, the error is pretty hard to notice, and if you wrote buggy compositing code, you might not have noticed that you had made a mistake at all. So let's move on to a much more simple example. Let's say you have a color, like the one on the left, and you want to find a corresponding color that is of the same chromaticity, but half as bright. A naive programmer may simply divide the RGB values in half, but this would actually be incorrect. In reality, having luminance is not equivalent to having RGB values, because RGB is a nonlinear color space. A linear increase in an RGB value does not correspond to a linear increase in luminance. This is not a very obvious fact. Without domain-specific knowledge of the sRGB standard, it's easy to mishandle color data entirely. So in summary, color programming is incredibly error-prone. Programmers need to keep track of the color space of data manually, and domain-specific knowledge is required to avoid errors. Errors that the programmer does make results in subtle data corruptions, which makes debugging color programs particularly difficult. The fundamental cause of all of this grief is that colors in image data are often represented as just array data. Therefore, array operations that are mathematically permissible but physically meaningless are run without issue. The other motivation behind CoolerSpace is performance optimization. it's easy to forget just how large image data is. Take these parrots, for example. This full HD image, 1920 by 1080p, takes up 5.93 megabytes uncompressed. And full 1 minute, 60 frames per second full HD video takes up even more space, 21 gigabytes to be precise. With such large input sizes, even minor optimizations yield pretty tangible runtime benefits. Luckily, there's a potential solution. We can view image data as tensor data, as people already do in the machine learning field. And this image can simply be represented as a 1080 by 1920 by 3 tensor of float 32 values. And since there's a large body of work on tensor algebra optimization due to the fields relevance to AML, they're swimming with money. If we compile color programs down to a tensor algebra intermediate representation, we can effectively piggyback off techniques developed in this field to optimize our color programs too. Finally, let's get into talking about CoolerSpace. So CoolerSpace is a Python metaprogramming library. Users write Python programs using CallSort library, and we type check those user programs. If they do type check, we compile them to ONNX, which we are using as a tensor algebra intermediate representation. We then use equality saturation to optimize these ONNX graphs, and the resulting ONNX graphs after equality saturation can be compiled further or run with arbitrary inputs using ONNX runtime. I want to first focus on the compilation stage. So the goal of the compilation stage is to use types to statically enforce color program correctness and to reduce the amount of boilerplate code a user needs to write. As discussed earlier, a major cause of color programming errors is the fact that color data is often represented as raw arrays with no information about encoding. In CoolerSpace, object types are a cross product between the physical type of the data and the dimension of the data. We use the term physical type here to refer to the type of color data that is represented by an object. Here's a graph of the physical types CoolerSpace currently supports. The nodes of the graph represent physical types. So it's important to note that CoolerSpace's physical types do not only include different color spaces like sRGB and OPRGB. And we also support data in the form of light reflectance and absorption spectral data. Yeah. So the edges of this physical type graph here represent valid conversions. For example, the edge highlighted in orange represents conversion from LMS space to XYZ space. And that's also represented in the equation on the left. Color spaces are often defined in relation to other established color spaces, hence the web-like structure of this graph. Let's take a look at how our type system can alleviate programmer burden while preventing common color programming issues. The example program above calculates the sRGB value of a spectral distribution of light. The line highlighted initializes an object of the light spectrum, and this expression tells CoolerSpace to cast the light spectrum to sRGB space. So CoolerSpace only type checks the casting between physical types if a path exists from the source type to the destination type. In our case, there does exist a string of transformations that we can utilize to convert a light spectrum to an sRGB value, hence the program type checks. Behind the scenes, conversions from light spectrum to LMS to XYZ to sRGB are chained together to perform the casting without the user needing to worry. So in this example here, a programmer is attempting to calculate the light spectrum corresponding to an LMS value. LMS is a three-dimensional color space, while light spectrum is a high-dimensional color space. Therefore, there cannot really exist a transformation from LMS values to light spectra. Such an operation is severely underdetermined. In fact, there are an infinite number of light spectra that correspond to a single LMS value. Therefore, the type checker rightfully rejects this code snippet. For our next example, let's say you're trying to do some simple arithmetic between two colors. In this case, just simple interpolation. Seen here, but the problem is that they're represented in different color spaces. This is a mistake, the same mistake that the faulty image compositing implementation made from earlier. But luckily for us, our type system specifies that arithmetic may only occur between colors of the same color space. Therefore, this bug does not pass the type checker's scrutiny. The luminance example for earlier is also remedied by our compiler. And recall that in many color spaces, there is some form of nonlinearity, like an sRGB. So when a user specifies that they would like to do any arithmetic on color data, our compiler performs said arithmetic in linear space, with the caveat of perceptual spaces, but that's a bit outside the scope of today's talk. So our succinct CoolerSpace code above is equivalent to the NumPy code below. In the NumPy code, the nonlinearity of the sRGB color space must first be removed. Then the user-specified operation occurs. Then the nonlinearity must be reapplied. In CoolerSpace, This code is actually all handled for you behind the scenes. It's worth noting that not all color spaces are nonlinear, and that different color spaces are nonlinear in different ways. Therefore, our compiler makes use of the color space information of the object to correctly apply and remove nonlinearity. Next, I want to briefly touch upon our optimization process. As mentioned before, we can represent color programs in the language of tensor algebra. We can therefore use techniques that have been proven to work on tensor algebra, like equality saturation, on our color programs. We choose to use equality saturation as our optimization technique of choice in this paper, as our programming model is quite high level. Due to CoolerSpace's quite strict type rules, users can't directly write the optimal implementations of many color science algorithms. Therefore, we have opted to use an expensive but effective state-of-the-art tensor algebra p-pole optimization method. But also, please note that CoolerSpace is not bound to equality saturation. Compiling down to a tensor IR enables us to make use of many tensor algebra-specific optimization techniques. So take the following example code. This is code for a naive implementation of color blindness simulation. And this code is compiled down to an ONNX graph, which we are using as a tensor algebra IR. Then the graph is serialized and passed into egg, an equality saturation framework. Egg uses our custom rewrite rules and cost function to search for an optimal ONNX graph. This ONNX graph is then passed to ONNX runtime for constant folding. Egg is capable of performing constant folding, but since color science data is so massive, and since egg operates on string inputs, it's not very economical for us to perform constant folding using egg. Instead, we modify our cost function such that the operations that are pre-computable are assigned a cost of 0. This allows our implementation of equality saturation to effectively still utilize constant folding. Finally, we arrive at our optimized ONNX graph. It's much more succinct and much faster to run. So we benchmark CoolerSpace against a handful of programs designed to test the entire gamut of CoolerSpace's current feature set. We first measured compilation and optimization time by benchmark program. In our experience, compilation and optimization time overheads were consistently insignificant across all programs. We also ran our benchmark programs with varying input sizes on both our optimized and unoptimized executables. We found a geo mean speed of around 15% across all programs. And in the best case scenario, we found around a 44% speed up. So we also tested our benchmark CoolerSpace against existing Python solutions, including Numba and color science. But what is it? Sorry. My screen died here. We found that CoolerSpace was consistently faster than existing solutions, but this is almost certainly just due to our difference in technology stack. CoolerSpace isn't bound by the limitations of the Python interpreter. Therefore, we don't have to consider that overhead. In fact, we even benchmark our unoptimized CoolerSpace executable against the other existing solutions. Rather, here we prove that CoolerSpace is able to guarantee type soundness and correctness guarantees without extra cost to the user. Here's a list of sources that I used during this presentation, and here are some useful links, including our GitHub repositories and Python package index links as well. And down there are a list of emails, but the one that you should probably pay attention to the most is this one, because that's where you will be sending all your internship opportunities. Thank you very much.
Wait, stay for questions.
Sorry. Yep.
Any questions?
Hi, I'm Adrian Sampson from Cornell. This is a very nice talk. This is very cool. I was just curious if you encountered any precision issues with the optimization. So there's like rewrites that would be true on the reals, but this is a fixed point representation. Do any problems come out?
No, it was a floating point.
Floating
point, and yes, we did encounter instability issues. We solved that by removing a few equality saturation rules that had to do with the power, manipulating power operators. We found empirically that solved most of our issues.
Thank you.
Thank you for the talk. A really cool project. I think the verifications has been much needed. My question is there any plan to allow people to write CoolerSpace code in a language that has a type system expressive enough to not require a meta compiler?
None yet, though we're certainly open to the idea.
Cool, thank you.
Any other questions?
Hi, I'm Jesse. I'm curious about the use of equality saturation. In particular, you showed sort of unoptimized and optimized, but I'm curious if you just removed that step, like how crucial was that step to your final performance results?
Well, you mean unoptimized versus optimized executables or ONNX graphs? If we removed equality saturation alone? Oh, yeah, it's pretty crucial. Pretty much all of our speedup comes from equality saturation because it turns out that constant folding with just ONNX runtime can't really be done unless you reorder the operators in a way that's palatable to ONNX runtime.
Okay, thank you.
All right, I have a question about the language and type system. So the examples you showed, I gather that expressions have sort of concrete types in terms of the color spaces. Do you ever have programs where you want a polymorphism? Is there polymorphism in the, like parametric polymorphism in the language and type checker where I could write something that works for any color space, or are there no such functions that work for any color space?
No such functions.
There's
yet.
no such functions. Oh,
sorry.
Okay. That is interesting. Okay. Any other question? Okay, great. Well, let's thank Ethan one more time. Thank you.